So we're talking about heat, and I just want to highlight some heat concepts because, again, we use a lot of these words incorrectly and interchangeably just in common parlance. Um, and we talked a bit about specific heat, which is more or less what's going to be going on here. But imagine the following scenario that you're probably pretty used to is it's a hot sunny day and there's a car parked out in some parking lot. It's been there for a long time, so it's at equilibrium. Just to put some numbers on it, we'll just say that it's like 40 degrees Celsius out, which is pretty dang hot. That's over 100 Fahrenheit. And the car's been sitting there long enough that the sun has done what the sun's able to do. And you know that when you walk up and you start touching the car, that there are parts of it that you do and you don't want to touch. And the way that we talk about it usually is you say like, oh, like the metal is really hot. The glass is pretty hot. The plastic isn't as hot. And the rubber, if you were to touch the dirty tires, the rubber isn't hot. So that's not true, right? Because in fact, this is all at thermal equilibrium. The whole thing's been sitting in the parking lot for long enough that it's all at 40 degrees. So really what is the mystery of the fact that there are certain parts of the car that you do and don't want to touch? So this, is related to and is most closely encapsulated in what we've been talking about as heat capacity. It's really something related called the thermal conductivity, how fast heat flows out. But you get a really good sense of what's going on in the following way. So remember that the heat capacity of something is the energy it takes to increase it by some amount of temperature. So we have heat, and that's energy, is C times mass. The amount of mass, more mass means more energy to heat it up, times the delta T. And heat's always considered to be flow, so there's like an implicit delta there, I guess, in some sense. And if I were to list some numbers, what I get is that C steel in SI units, it's about 450. We get joules, and it costs degrees Celsius or Kelvin, kind of doesn't matter. So those are the right SI units for a heat capacity. And let's just say that, you can tell that I learned how to draw cars in my childhood in the late 80s or early 90s because they're really boxy. So let's go all the way in on that and say it's got some wood crap on it, like a interior paneling, I don't know. And the heat capacity of wood's about 1,700 joules per kilogram degrees Celsius. And roughly speaking, a human has a pretty high heat capacity. We'll call it 3,500 joules per kilogram degrees Celsius. Okay, so why does the steel feel hot and the wood less so much? Again, it's not that they're at different temperatures. It's the fact that it's easier to change the temperature. It requires less energy. Whereas you, with your hand, when you touch something, it takes a lot of energy before you're going to come to thermal equilibrium with that 40 degrees. So really the person to blame isn't necessarily the steel. The steel's being like pretty compliant and giving up its energy to heat up your cold hand. The real issue is the human. So really this isn't a temperature thing. This is a heat capacity. Or again, we'll talk a little bit about heat conductivity, which has to do with rates of change. But really this is the issue. And let's talk about heating all of these up by, a kilogram of these things up by 20 degrees Celsius. To put some numbers on this and, again, show off how to use this formula again. And we've seen this a couple of times because this is a delta T, an increase in temperature. Celsius or Kelvin would be equally okay to use. Okay, so the heat for steel, so I want to raise 1 kilogram of steel, which has a heat capacity of 450 SI units. I'll draw them really small. By 20 degrees Celsius in the Kelvin, no problem. Multiply that out, I get 9 kilojoules. Do the same thing for wood. And again, because it's a delta, you can interchange, or you will see Kelvin and Celsius just kind of liberally interchangeably used. And then that gives us 34 kilojoules, kilo meaning times 10 to the third. And then I'll leave off the units, human. That would be 90 kilojoules. Because it's got this 3,500, is that right? 70, sorry, 90. 70 kilojoules. So really the issue of the person putting their hand on the metal is, again, the issue with the hand is that it's going to require a lot of energy to heat this hand up. So that's what you're really experiencing when you touch a hot car. Don't blame the metal, blame you for requiring so much energy to heat yourself up to thermal equilibrium. So this is C, and basically you look it up and you're a little bit mindful about the units. C is okay, degrees C, degrees K is okay. If you get Fahrenheit, you just got to multiply or divide by 9/5 appropriately. So I'm just going to quickly list some issues in the real world. One is that obviously, especially when you consider water, we could have phase changes. So phase changes just throw everything off, and you should never, not for a moment, think that the heat capacity of water is the same as the heat capacity of ice, or in fact that there's even a heat capacity for steam. There's an infinite number of heat capacities for steam. So phase changes are a problem. And phase changes change C by a lot. So specifically, C ice is not equal to C liquid water, which is not equal to C steam. And in fact, the third thing we'll talk about is the fact that there really isn't a C steam. So gases, all sorts of funny stuff happens. Secondly is if you look at things over a big enough distance in temperature changes, really the heat capacity should depend on the temperature a little bit more than we've neglected. So for instance, if I looked at like lead, so I looked at the heat capacity of lead and I went from pretty dang cold to pretty dang warm, it might actually look something like this. So there will be a change in behavior even in the solid phase. So I'm talking about solid lead before we liquefy and it changes. So what will happen is the two things that you can do to keep yourself from getting in trouble with this is use small delta T's. If you're using 10 degrees or something, totally fine. And if you're using 500 degrees, maybe you want to actually worry about this. So unfortunately, it turns into a calculus problem. And the second thing you can do is make sure that C is valid in that temperature range. So if you look up, for instance, the heat capacity of lead really close to its melting point, but you have this at like 10 degrees above absolute zero, you might actually be using the wrong C. So, and then finally, I shouldn't say don't use, but be careful about gases. And I'll just state it as a caveat now. We'll actually dig a lot into this in about a week, is that the thing that's happening with solids and liquids is that you're always doing these things at, roughly speaking, constant volume. But with gases, you have a choice. So you could put heat in at constant volume, and there's a specific heat capacity at constant volume. Or what you could do is you could put in heat at constant pressure. And both of these are distinct processes. So, if you remember our piston, what I could do is I could heat this up and let the piston move back and forth, so that would be constant pressure. Or what I could do is I could fix the piston and put in heat, i.e. raise the temperature at constant volume. And there would be a different value of C for each of those. So I'll write them for water. We'll do a practice problem, and then I'll show you a pretty neat demo, which is kind of an excuse just to do that demo. So the constant volume and constant pressure heat capacity for water are, they're both small numbers in SI units, but just notice the difference in between them. So the percentage difference, it's quite significantly. And why not do this too? Let's just introduce or remind you that other units definitely exist for thermo. And 1 calorie equals 4.186 joules. And 1 kilocalorie, which is actually a nutritional calorie. So when you look at the back of food, it says calories, but it's really kilocalories. So a Tic Tac has 4,186 joules in it, which is kind of crazy, but it's true. So kilocalories, just another unit, be aware of them, they exist. So let's say that you have a kilogram of air in a sealed container. And I just want to know how much energy it takes to heat the thing up by 2 degrees Celsius. Okay. So sealed container, that sounds like a constant volume process, so that would mean that we use CV and not CP. So heat that goes in, C, this is a constant volume process. It's just really go nuts with the sub and superscripts. That's for air. We were told what air is. Mass of the container, and then delta T. And I'll just put down these units and take them seriously for a second, so see what happens. So CV is 0.18 kilocalories per kilogram degrees Celsius, and we have 1 kilogram, and then we have 2 degrees Celsius. So the kg and the C go away, we'd be left with an answer in kilograms, so that would be 0.36 kilocalories. And if you wanted that in joules, question didn't say make it joules, so I don't feel compelled to give it an answer in joules. You would multiply by 4,186. So basically just under 2,000 joules. Okay. For instance, if we had something in a container where the piston could move, so not constant volume, but always venting to the atmosphere, constant pressure, we would have a constant pressure process, and we would use CP instead, right? Hello. So this is totally not gratuitous and absolutely warranted demo. Has nothing to do with the fact that there's just liquid nitrogen sitting around this completely desolate building. And I'm going to do a thermodynamic process that you've probably seen before. And then we're going to figure out how much energy goes into it. This is actually pretty interesting in the sense that, it's not really obvious. You can see it boiling, I hope. That's pretty neat, huh? It's not really obvious what the numbers in thermodynamic stuff really mean, because sometimes they're huge, sometimes they're tiny. But I got some air and I've got some liquid nitrogen. The liquid nitrogen is at 77 degrees above absolute zero, and I'm gonna put the balloon in, and I'm gonna be patient, but not too patient. And we're gonna figure out how much heat the liquid nitrogen stole from the balloon. And because this is a gas, we have choices. Well, finally we popped it. Okay. Sometimes they live. I guess I left that one in for too long. So the first question is, because this is a gas, what heat capacity should I use? Should I use the heat capacity at constant volume, or should I use the heat capacity at constant pressure? And through the magic of telepathic time travel, I heard you all say this correctly, is that in fact this is a constant pressure process. So we have a liquid nitrogen balloon, and it basically disappeared. And we might actually revisit this. And the thing that's happening is this is always subject to atmospheric pressure. So pressure here is 1 atm, pressure here is 1 atm, or 101, 300 pascals in both cases. And it's constant. So if I want to know the heat that flowed out of the balloon, and again, we'll be casual about the deltas. This is always flow. In this case, it's leaving. We'll also be kind of casual about SIGN signs. So in this case, it's flowing out of, and I'll just say flowing out of. It's air. Like the crackle of the liquid nitrogen. I don't know if you guys can hear that. And because it's CP, we know that's 0.25 kilocalories per kilogram degrees Celsius. Okay, what's the mass of that balloon? So a little sidebar, until this is stuck in your head, it's worth going over and over. So the mass of the air in that balloon, I think it's about 0.5 liter. So what I really need is the mass per liter. And two ways of getting this. One is if you remember the mnemonic that 1 mole of air, or actually 1 mole of any ideal gas at STP, takes up 22.4 liters. Basically, we have what fraction of a mole, and then we also know that the molar mass of nitrogen gas is 28 grams per mole. So we have 1/2 of a mole, so that gives us, like 1/45 of a mole inside that balloon fixed. And then we have 28 grams per mole. So that would give us our mass. So mass of air would be about 28 grams per mole, and then divided by 22.4 liters per mole. And then moles go away, liters gone, and then we end up with 0.63 grams, or 6.3 times 10 to the minus 4 kilograms. Which is to say not a lot. Yeah, 0.5 gram's worth of mass seems, roughly appropriate for me, so that's fine. And we want kilograms in, so we gotta put kilograms in as the mass. And then, okay, we're gonna heat this, or cool this down. So liquid nitrogen's at about 77 degrees above absolute zero. So this thing started at about 270, or we'll call it like 280, I don't know, it's actually kind of chilly. 280, and then it ended up at about 80. So it didn't completely liquefy. So we'll just say that it lost like 200 degrees Kelvin, which is also losing 200 degrees Celsius. So that's pretty good for our estimate. And again, I'm saying heat flowing out, so we don't have to worry about a minus sign. And then, okay, Kelvin, Celsius, that's okay because it's a change. Kilograms, we're going to get kilocals out, which is fine. But let's say that I want joules. So I could convert this at either level. So I'll just do this and we'll get kilocals. Really, yeah. So I should write the answer for you guys. So 0.30315. And then multiply that by 1,000 to get calories itself, 31.5 calories. Notice these aren't nutritional calories. This would be like 1/50th of a Tic Tac, so that's like a pretty small amount, a little bit shocking. The thermo numbers are always bigger or smaller than you think they should be, which is kind of weird. Or in joules itself, 131.9 joules, which we put 1 sig fig in, so that's a bit gratuitous, but just to give you a sense of these numbers. Okay. So we have an important piece, the energy associated with the temperature change, and we have a couple of caveats to use it properly. So for gases, you need to know the details of the process, constant pressure versus constant volume, as two examples. And for solids and liquids, you know that you shouldn't take it, the constant nature of C isn't really a constant, especially over really big temperature changes. But with that aside, we basically have the thing that physicists really love to do more than just about anything else, which is to conserve energy. So we can do conservation of energy problems now, which are called calorimetry problems. And what distinguishes calorimetry from other conservation of energy problems is really that we just include heat. Okay. So let's imagine that I have two systems, system A and system B. And our next big topic is talking about the details of how they would actually do this, whether they exchange photons or I get them to touch or whatever. They come to equilibrium. And so what I know equilibrium is, in this class at least, is thermal equilibrium. Which is to say some process occurs that allows TA to be equal to TB. So that's what it means for them to come to thermal equilibrium. And then I can ask, well, how much energy do they exchange? So QB, just for the sake of argument and discussion, and what'll happen is on a practical level is you'll put the SIGN signs in by hand to make them work out right. But let's just say, for the sake of argument, that this thing cools down and this thing heats up. In that case, energy conservation says that the heat that system A loses is equal to the heat that system B gains. And that's really it. So the rest is just filling in the details, and we now know, again, how to do that. So loss of heat from QA has to be equal to the gain of heat from QB. That is energy conservation. So we'll do basic problem now, and then what'll happen later is you'll kind of add like the bells and whistles, which involve phase changes and the specifics of how a gas might, for instance, come to thermal equilibrium. I'll write down the equation as we use it, because again, the way that you handle signs in a calorimetry problem to really make sure that you're not making any errors is just make the signs be whatever they need to be correct. So let's say that we ask this. And maybe some of you guys are tea drinkers, but maybe you've always wanted to know this. So you have like a nice thick ceramic mug and you pour the coffee or tea into it. And of course the mug heats up, but the question is how much does the mug cool down the coffee itself or tea? And the way that we now know how to do this is it's a calorimetry problem. So I know that, for instance, the heat that the coffee loses is equal to the heat that the mug gains. And because we have solids and liquids, so no freaky gases that we would have to worry about the specific nature of the process, whether it's constant volume or constant pressure, then I can just use, for each of these, C times M times delta T equals Q. So this is kind of like the proto formula that we'll use for each of these. And we'll have two different aspects to it. So we'll have, we got to figure out what the mug is and what the coffee is. So maybe you have your own choices about this. I'll put down some reasonable bits of information and approximations. So mass of coffee, maybe like a full 8-ounce cup of coffee is about 150 grams. We can probably say that coffee is about water. So actually, sorry, let me make this a little bit more. So I'll put 250 grams, like a nice big cup. I'm going to use mug, aren't I? M is a little bit weird. Yeah, we'll roll with it. Okay, so the specific heat of coffee or tea, don't get confused by the fact that it's dark in color. It's essentially water. So it's, water doped with psychoactive chemicals. So I'm actually going to say that this is water. And water has a specific heat in SI units of that 41 Celsius. So essentially this is water. And you could probably round it off to indicate that it's, a little bit, probably less than water. Okay, and then what I need to do is make some assumptions about the temperatures. So we'll say the initial temperature of the coffee is equal to, 90 degrees Celsius. I'm sure I'm offending somebody who knows the perfect temperature for a pour over, but you can get over yourself. And now what we need is the mug. So this I would probably have to look up. I don't necessarily know this. So the mass of the mug, we'll call that about 150 grams. So maybe like a really thin ceramic mug and a really big cup of coffee. I would look up ceramic. So this I would really have to look up. And something like clay, fired clay, has a specific heat of 840-ish is what I found. And then we'll say that this thing starts at room temperature. So it starts at 20 degrees Celsius. Okay. And now we have all the pieces. The question is just arranging them in such a way that we get the signs right and we're not making any, kind of grievous errors where we have energy flowing from the cold thing to the hot thing. In fact, there's a law of physics that tells us we should do that. Probably one of the last laws of physics you ever learn. Okay, so the way that I'm going to do this is just verbally write this again and just make sure that everything in this case is positive. I can't have a positive number equal a negative number. So what this loses and gains means is that a positive amount lost and a positive amount gained, just everything's positive. So the signs are in the kind of verbiage of losing. So we have this. And now we have C coffee, delta T coffee, C mug, M mug, delta T mug. Okay, so the two things that we know is that energy is conserved. We wrote that. It's heat energy. We're not doing any other sort of energy. We're not dropping the coffee to give it some gravitational potential loss. The second thing we know is that thermal equilibrium means that the final temperature is the same for each. So that's the statement of thermal equilibrium. And now I can explode these deltas into the initial and final. So I have specific heat of the coffee, mass of the heat of the coffee. This is where I might get into trouble with SIGN sign. And I'm going to make all the things I need to make positive, positive. So the coffee starts hot and ends cold. So using the same notation, C naught minus, they're both final, so I'll just say F. They share that final temperature. Okay. And then that's positive because it starts hotter than it ends. I need to make this positive too. So in that case, the delta would be it starts cooler than it ends. So that would be TF minus T naught mug. And then I can start dumping in numbers. So we have C coffee, about, I did everything in SI. So I'm going to take professor privilege and just drop units, saying just they're all SI units. So 4186, mass of the coffee cup. Sorry, got to put the masses into SI units, so that's 0.250. And then delta T, because it's a delta, Celsius or Kelvin are the same, so that really is SI units. So we're going to have this be, we start at 90 degrees Celsius, we end at TF, and then we have 840, 150, 0.150 kilograms. And then TF, we still don't know, and then this starts at 20 degrees Celsius. Okay, this is one equation with one unknown. So you have to do some, probably the easiest thing to do procedurally is to divide all this stuff, and then you end up with the TF by itself. But honestly speaking, they're a little bit laborious. And you crunch through stuff, and I'm going to do this in 2 steps. So I'm going to actually multiply everything out and get you the thing that you see before the last step, just as partly a checkpoint, but partly to point something out. So multiplying and then isolating TF, I something that looked like this. Where I would get some number joules per Kelvin. That's what multiplies this. So this turns out to be joules per Kelvin. We got rid of the kilograms. And then the other side would be joules. Just to highlight the fact that this really is an energy conservation problem. And then finally get this TF is 82.5 degrees Celsius. Okay, so tactically speaking, we made use of the fact that this is yet another delta T. So delta T in Celsius and delta T in Kelvin are the same thing. Looks like we lost about 9 degrees, 8.5 degrees from our coffee cup pouring it into the ceramic, but doesn't seem like the worst thing ever. These are the 2 bits of a calorimetry problem. Is We conserved energy. Heat is energy. We know how to account for heat energy. And we use the fact that equilibrium occurs when the temperatures are equal. So really, that's kind of it. We'll add a couple more bells and whistles with phase changes, but you'll do a bunch of these. And basically, the bigger story is don't be afraid to just mar an entire piece of paper working through the details.